Inequalities involving absolute value. Notice that the absolute value bar is representing what number is having a distance away from 0. And in the example here, greater than or equal to 3. So let's look at a couple examples so you can see how we'll do these problems. Just like with the absolute value equations, we're going to need two cases here. One where the number is positive and one where the number is negative. But also keep in mind that when we switch the sign of the number, we're also going to switch the direction of the inequality sign. So in example 1a, I'm going to keep, for case 1, I'm going to keep what's given, just minus the absolute value bar. So 3p minus 12 is less than 9. For case 2, I'm going to keep the 3p minus 12 the same, but I'm going to flip my inequality sign to greater than, and I'm going to change the 9 to negative 9. So it becomes the opposite sign and opposite inequality sign. Some people that have used keep, change, change in the past like to go with keep, change, change. So to start solving, we'll add 12 to both sides. Divide both sides by 3. P is less than 7 and P is greater than 1. Okay, and so this is actually, because of the less than sign in the original problem, this is going to be an and. And so one way that I remember that is less than, if that helps you. And so we're going to need a compound inequality. Whenever there's an and, you're going to want to write it as a compound inequality. You take the smallest number, less than the variable, less than the larger number. This is going to be an intersection. I like to call it an intersection because it helps me remember that any less than or and is going to be an intersection. And the graph will look like this. Keep in mind it's open circles since it wasn't equal to, it was just less than, not less than and equal to. Example 1b, we're going to isolate the absolute value bars first by subtracting 3 from both sides, and so x is less than 9. Now I can create my two cases. Now that the absolute value bars are isolated, I can create my two cases. So x is less than 9, and on the other side, x is, we're going to flip the sign to greater than and change to negative 9. This was also a less than, so this is going to be an and. And so I'm going to write my compound inequality, small number, less than x, less than large number. I'm going to extend this graph here. Let's just call this negative 9 so I can graph this. So open circle at negative 9, open circle at 9, and this is an intersection. I'm going to go back to example 1a here. I like to write this as a solution set. So for every value of p, 1 is less than p, which is less than 7, would be the proper way to write that answer. And for example 1b then, for every value of x, negative 9 is less than x, which is less than 9. Now I said the graph would just be an intersection, but I want to explain why that worked. So for instance, if I look back at example 1a, p was less than 7. So if I were to graph that by itself, it would look like this, less than 7 going in this direction. And p is greater than 1. Well, that would be open circle at 1 going to the right, greater than, and notice they're crashing into each other here, and that's why we have that intersection. Okay, in example 2a, our absolute value bar is already isolated, so I can write my two cases. The first one would be x minus 5 is greater than 4. My next one would be x minus 5, flip the inequality sign to less than, and change the 4 to negative 4. And since this started as a greater than symbol, that's going to be an or. And I like to call this greater than. So I remember that if it's greater than, it's going to be an or answer. Okay, I'll show you what that means more in a minute, but what's going to happen here is we're going to solve these for x. X is greater than 9, and x is less than 1. Remember, it's going to have an or in between. So x is greater than 9, or x is less than 1. Let's see what that looks like on the graph. So x is greater than 9, or x is less than 1. They actually kind of look like oars on a boat, if you think about that. Like on a canoe. I won't even attempt to draw it for you. Okay, in example 2b, I want to isolate those bars first. I'm going to add 3 to both sides. And so now I have absolute value of x plus 2 is greater than or equal to 10. It's still a greater than. It's an or statement. Okay, so I can write my two cases. X plus 2 is greater than or equal to 10, and x plus 2 is less than or equal to negative 10. Subtract 2 from both sides. X is greater than or equal to 8, or x is less than or equal to negative 12. To fix my solution sets here. Okay, so x is greater than or equal to 8 would be a closed circle going to the right, and x is less than or equal to 12. Negative 12. Can't read what I wrote. Let me extend my graph a little. So that's negative 12. Okay, so that would be a closed circle at negative 12 going to the left, less than. Again, it looks like oars. Okay, example 3. The average depth of a river is 4 feet. With rainfall and evaporation, the depth of a river is within 0.25 foot of the average depth. Find the range of depths for the river. Just keep in mind that with absolute value equations, the give or take amount, the amount that varies, is what comes after the equal sign. In this case, it'll be what's after the inequality sign. And if it's within, think about that as like an intersection. Within would be like an intersection. It's going to be less than, which is an and. So this is going to be a less than. Within, inclusive here would be including it. So we have to have an equal to bar. 0.25 and x minus 4 is what's in between our absolute value bars. Okay, and we can write our two statements, and this might make more sense when we do this, our two cases. So x minus 4 is less than or equal to 0.25, and x minus 4 is greater than or equal negative 0.25. So I changed the inequality sign and the sign of the number. I'm going to add 4 to both sides now. And I end up with x is less than or equal to 4.25, and x is greater than or equal to 3.75. So this was an and, so for every value of x, small number 3.75 is less than or equal to x is less than or equal to 4.25, the big number. And that's my solution set for example 3. Just like with absolute value equations, there's special circumstances. So remember with absolute value equations, you could never have an absolute value be less than a negative. So if I had a problem like this, for instance, the answer would be no solution. With absolute value inequalities, we have to keep in mind, like I said, absolute value expressions are always non-negative, and when solving absolute value inequalities, you may get the following solutions. It might not just be no solution. We could also have this other circumstance where we have all real numbers. If a statement's true, it's going to be all real numbers. If a statement's false, it's going to be no solution. So let's take a look at one. So in the first example, whatever's in the absolute value here is going to be positive. And here's where I have my negative number, and so that's kind of like a red flag to me here, because I shouldn't have a negative number. There's no way that absolute value will ever be equal to a negative. But in this case, since it's a positive where the absolute value is, could a positive number be less than negative 10? Since this would never happen, the solution is going to be no solution. If we look at the next problem, this part that's going to be positive is greater than or equal to negative 4. Again, that negative there was a red flag to me, so this is why I'm checking this out. So since the positive will always be greater than negative 4, this is always true. The answer is going to be all real numbers. So you can't graph no solution, but for all real numbers, if you want, you could put a continuing line going on forever if you were asked to graph that.